I noticed it says that Morgan Herlocker is giving this talk. And if you've met Morgan, then you know that I'm not actually him. So I'm Tim Channel. I've worked at Mapbox for about 9 months. Started there last August. I work on our telemetry pipeline, mostly working with GPS data that we get from partners or our mobile SDK, trying to figure out how to improve our map from GPS data. But I also work on a lot of analysis in that process, and a lot of it uses TileReduce. So TileReduce is fast parallel spatial analysis on vector tiles in JavaScript. Well, Node.js. We talked about browser use cases, but there was never really a big need for it yet. Like you might have some, there's an OSM analysis task right now where people are using TileReduce to analyze edits over large areas over time. But that's using TileReduce in the back end, using server calls for that. And that's actually worked out a lot better. The amount of data you'd need to load in your browser to do the analysis is a little bit silly. So why did we pick Node.js instead of something else? So we found that the computation was fast enough versus Python. JavaScript is algorithm friendly versus writing it in PostGIS, which I'll come back to in a second. And it's got great package management versus a lot of stuff we've written in C or C++ before. And there's about a zillion libraries already versus pretty much anything else out there. Specifically when looking at PostGIS, a bunch of us at Mapbox have done some PostGIS in the past. It's still a really important part of our business. But it takes a certain mindset to be able to unwrap spatial algorithms into SQL queries. And we found that you would spend potentially days planning out or maintaining these analysis tasks, whereas everybody on our team already knows JavaScript. So we started with where we already had the knowledge, and anybody on our team could quickly get on board with TileReduce. So one of the strengths of Node.js is that it's got a single-threaded event loop. That's great when you're talking about I/O or non-blocking operations where you can spread out work using async calls. But when you're doing something like heavy data analysis, which is almost entirely blocking calculations, that means your cores are spending a lot of time waiting around, doing nothing. TileReduce distributes spatial analysis using all of your CPU cores. So by default, the TileReduce process will use one worker for each CPU core available. That means if you're using it on something like a C3, EC2 on AWS, you can have 32 worker processes or more. And it makes good use of the CPUs. So you can give TileReduce an area to do analysis on vector tiles, and it'll automatically split up the job. Each tile will get sent to workers in a queue, or tiles can be read from all the available tiles in an mbtiles. So if you're looking at vector tile analysis, you can specify one of your mbtiles to be a source for the list of tiles. This is useful when you're comparing two different data sets that have different areas. For example, if you've got OSM planet data and you're comparing local, state, or county level data to it, you can process only the county level data by specifying the county mbtiles as the source of tiles for processing. So next up is the map, but not the kind that you look at to figure out where you are. Each tile is processed through what we call a map script. TileReduce gets its name and a lot of its inspiration from MapReduce, this concept where you have a list of things to do, and you map a function over them, and then you reduce the results of the map functions. We don't strictly adhere to MapReduce. TileReduce uses an event emitter. It's not technically functional, but it's there in spirit. So the map function is where you get all of your work done. This is where we'll do any counting, processing, aggregating, and whatever processing needs to happen. So the types of data sources that we're using are explicitly Mapbox Vector Tiles. We've kind of talked a little bit about doing some raster analysis in TileReduce, and There have been like some sort of like hacks onto it to be able to do that. It's a little tricky, but it's something that I think is going to be definitely powerful in the future. We can work in raw or GeoJSON in the map function. So raw is vector tile.js. The benefit of using vector tile.js is that geometries aren't decoded up front. So if you need to filter data before processing, you can really quickly pick out data without wasting time decoding all of the geometries. GeoJSON is available as well. The benefit of that is it's a lot easier to work with. We can work with remote or local tiles. Remote tiles can be hosted on a tile server like Mapbox that returns vector PBFs. And local tiles are just mbtiles. The benefit of using local tiles is that they're much faster. You don't have to worry about downloading every single tile. And you don't have to worry about accidentally DDoSing your server if you don't have rate limits, which we didn't at first. In order to scale beyond the number of CPUs on your computer, you can easily add more computers. If you use a low zoom tile to set up your jobs and pass that to each of your individual computers, TileReduce will split up that low zoom tile into smaller tiles, do the job, and then you can unify all your results at the end. An example is if you're analyzing data at zoom level 14, you could use maybe a zoom level 5 tile to specify your jobs, send that a zoom level 5 tile to each of the worker computers, and then get all the results back. So the way that Mapbox is using TileReduce is largely in analyzing OpenStreetMap. We're looking at, like you can see on the screen, changeset analysis, finding bogus data where people have mislabeled things or things don't make sense. Vandalism detection, that's kind of a big one that we're pushing on now, trying to find areas where people have moved data a really massively significant changes. Like if you take a road and you move it 10 kilometers over, it's probably not the same road anymore. That might be a mistake, or it might be somebody just messing with the map. We also have seen things where people rename landmarks to the name of their business, free advertising in OSM, things like that. Machine learning is one that we're kind of poking on. The tile model is pretty interesting for machine learning. You can split up the work really nicely that way. Automated mapping, such as this animation in the background where we are highlighting a road that isn't mapped in OSM. And the good thing about doing this in TileReduce is that it scales globally really fast. One of my early jobs working at Mapbox was detecting footways in OSM which weren't labeled as sidewalks, even though they acted as sidewalks. And this caused issues when we were trying to render the data. You would be looking in a city, and then you would see a sidewalk next to a road that was rendered as if it was like a trail in the middle of the woods. The styling would kind of throw it off. Anybody in OSM will tell you that you don't map for the renderer, but in this case it was some missing context. The thing in the real world is a sidewalk, but it was never tagged as one. So we used TileReduce to scale this up globally, and we could find all of the mistagged sidewalks in about 20 minutes. Another example is using Runkeeper. We get trace data from Runkeeper in the past, and we use that as vector tiles. We compared it to OSM, and we found tracks where people were running that weren't mapped in OSM. So what's weird about TileReduce? I think this is an important thing to talk about whenever we're talking about a technical tool. There's always something that doesn't work how you expect. One of the things is working with vector tiles is a little bit interesting. Vector tiles were originally built for display, and we're using them for analysis. So you have to be careful about how you generate vector tiles. When working with TileReduce, you don't want to use too high of a zoom. For example, we originally were working on zoom 15 or zoom 17, I don't remember, OSM tiles, and on a technical level, this resulted in too many inter-process calls. It actually got slower because the tiles were zoomed in too much. processing more data per tile was cheaper than sending more tile processing requests. So we ended up generating our OSM tiles at zoom 14 instead. Another of the weird things is also related to vector tiles. Vector tiles usually have buffers to prevent errors in rendering. So you'll have an area around the current tile's specified location where you have data from the next tile over in every direction. This is great for rendering because it helps you reduce errors where lines are disjointed and things disconnect when you zoom. But during processing, this means that you're going to be doing extra work, which is wasteful, and you're also going to be duplicating effort in terms of counting things. So if you're counting the number of miles of road in the area and your tiles have buffers, you're going to be counting data that's in multiple tiles. So we specifically generate tiles that don't have buffers. We also have to worry about simplification, which is key for visualizing vector tiles, but not for analysis. And then, like I mentioned before, another weirdness is that TileReduce isn't actually MapReduce, even though we kind of stole the lingo. So it's available on GitHub with a cool, shiny GIF in the background. And I have a really quick example. I'm not going to go super in-depth here, but OK. So every TileReduce script is made up of two pieces. There's the index or reduce file where you kind of set things up and then you aggregate all the results that you get back. So this kind of section here is all your setup. And then down here is all of your actually getting data back. So we set up a source that is OSM tiles for Cuba. I picked Cuba because it was small and easy to download on the hotel's network. And what we're saying here is that when we get back reduce events, which means the data has been processed, we'll take the result and then just add it to our total. So what we're just going to do is sum miles of road. And at the end, we'll log out all the miles. So this is the map script, like I talked about earlier. Kind of doesn't fit very well on the screen. So what we're doing is we're iterating over all of the features. I'm using GeoJSON here in a particular tile. And if it's got a highway equals motorway tag, then we'll calculate its length. And then at the bottom here, we'll send back the miles. So we calculate the length, add it to the total miles for the tile, and then send it back with this callback. So in action, I'm logging out all the data just so I can see it. We get a number at the end there. You can also just log out your data to a file, which then you could tile up again and stick on Mapbox Studio so you could look at where all of the roads on Cuba are. Okay, any questions? Over there? Yeah, so the question was whether we thought about adding more processes than there are cores to take advantage of threads and scheduling work on a single core with multiple processes. We kind of tinkered on it. We found out that in a lot of cases we would end up kind of stalling if we were too aggressive with it. So finding the right balance is a little bit tricky. So I think we erred on the side of caution and said, we'll just go with how many processes there are. They stay pretty busy, so the gains would probably be minimal unless you're doing a really heavy job that you want to eke out as much power as you can. The question is whether simplification is a big issue in processing. We use Tippecanoe for generating tiles most of the time. We'll have GeoJSON sources or convert things to GeoJSON if we need to, and then turn them into vector tiles with Tippecanoe. And there are options to turn off simplification. So aside from simplification that happens by nature of how vector tiles work, which includes a little bit of rounding, mathematical error, but it's pretty precise, we usually turn it off for analysis. Can you speak up? Performance compared to Spark?
Yeah.
Okay. I don't know that we have looked at Spark. I think it's been investigated in the past, but I haven't looked at the results myself. I can tell you that we were pretty happy with TileReduce when we first built it, and TileReduce 2 would take something on the order of close to a day to run a global job on an EC2, and TileReduce 3 does it in like 12 to 20 minutes. So we're pretty happy with that performance already, and we're pretty happy with the maintainability.
Spatial data has such an uneven distribution, sort of like that slide there shows. So just wondering what sort of considerations favor a square tiling where all tiles are the same size versus maybe more balanced or density-based distribution.
Yeah. Technically, it might be possible for us to. So the question was first whether using tiles of the same size for analysis, given that data is unevenly distributed, is the best way to do it, basically. So I think technically it would be possible using vector tiles to only use zoom levels that are most appropriate for the data, but we haven't tried that out with TileReduce. It would take a little bit of hacking. We've found that it's really not been prohibitive for us to use a single zoom level for the data. If there's not much data in a tile, because you're using a large tile, you didn't waste too much time because there's not much to process in that tile. You wasted the message to the worker. But that's not that big a deal unless it's like all of your data. Okay. All right.